Okay, I'm making a tragic flaw in the world of teaching mathematics right now, but we're going to go with it. I'm going to do some examples on optimization from your textbook. So hopefully you have your book open and you can look at the problem. I'm going to start with number 2, maximizing area. Now I have a list of suggested steps for you, but really the bottom line is you just have to do a million of them, and they're not all going to be the same. Sometimes none of them are even going to be the same, but you just have to do your best and see what makes sense. Where is my list? Here is your strategy. Pause it, read it, write it down. Bottom line, you're going to write an equation that hopefully only has one variable in it, take the derivative, and then either find the maximum or the minimum. So you're going to set your derivative equal to 0. That's the bottom line. Try to rewrite it so everything's in terms of one variable, take the derivative, set it equal to 0. So let's go. Question number 2 on page 230 says, what's the largest possible area for a right triangle? So I'm going to draw my right triangle, whose hypotenuse is 5 centimeters long, and what are its dimensions? So we want to maximize the area. Remember, area of a triangle is 1/2 base times height. In this case, I don't know the base or the height, but I'm going to call this b and I'm going to call this h. So I know that b squared plus h squared equals 25. So now I can solve for one of these variables in terms of the other. I'm going to say b squared equals 25 minus h squared, and b equals the square root of 25 minus h squared. Now again, normally we do plus or minus, but we're talking about a triangle here, so you're not going to have a negative side length. So this is an h, that's a b. So back up to my area. I have area as 1/2 b. I should have solved for h, sorry. I'm going to replace b with what it's equal to, and then a of h. There's my area. Take the derivative of that. Well, let's decide, do we want to simplify it first? Nah, we'll take the derivative. So a prime equals 1/2 times product rule. First times derivative of the second is simply square root of 25 minus h squared. Plus second times derivative of the first is h times, now I'm going to write 25 minus h squared to the 1/2 to make it easier. So h times 1/2, 25 minus h to the negative 1/2. Okay, so there's my derivative. We need to know when that equals 0. So let's simplify. So first I'll set it equal to 0. And if you recognize, if I put a 0 here and multiply both sides by the reciprocal of that, that constant goes away. So I'm not even going to write that. So pretend I multiply both sides by 2. 0 times 2 is still 0. The 1/2 is gone. So now we have square root of 25 minus h squared plus h over 2, and the square root of 25 minus h squared is down here, and that's a squared, and I forgot to multiply by the derivative of the inside, which is negative 2h. So back up, here's why you do problems ahead of time. When I simplify this, I have this negative 2 and this 2 cancel out to a negative 1. H times h is h squared. So this plus here is now a minus because I have negative 2 times 1 out here. Again, the 2's cancel. I have h squared times 1 over that, 25 minus h squared. Okay, I'm going to add this expression to both sides. I am going to cross multiply. So when you multiply this by itself, you get what's underneath. Add h squared to both sides. Divide by 2. And h equals the square root of 25 halves, otherwise known as 5 root 2 over 2. what is the question asking? What are the dimensions of the triangle? So h is, now remember in calculus you don't really have to rationalize, so I'll leave it as 5 over root 2 because that's easier. H, if it's 5 over root 2, then I can use Pythagorean theorem and solve for b by plugging in here. And then common denominator is 2, so it's square root of 25 over 2, which is also 5 over root 2. You will find in a lot of these that the maximum area is when the two dimensions are equal, but still have to do it, figure it out. I hope that made sense. I know it's hard, I know it's confusing, but basically the hardest part was figuring out that b is 25 minus h squared and plugging it in. The rest of it was just taking derivatives and solving. Let's try number 5. Inscribing rectangles. Figure shows a rectangle inscribed in an isosceles right triangle whose hypotenuse is 2 units long. And recognize that the hypotenuse is on the x-axis. So, express the y-coordinate of P in terms of x. So the height of that rectangle is whatever that function is. But it's just a line. So since P is on the right-hand side, we're only going to find it on the right-hand side. And the equation of that line is y equals 1 minus x. How do I know that? Because it's an isosceles triangle. So let's look at it. Looks like this. And if this is 2, then this, I know there's a formula for that, but I can't think of it. So let's just call these both, we'll call them x for now. X squared plus x squared equals 4. 2x squared equals 4. Oh yeah, root 2. That makes sense. So the length of this is root 2 from here to here. And then the y value, well, if this is 45, because it's isosceles right triangle, so I know each of these is 45, and these are each both 1, then I also know that the height is 1. So this point on the y-axis is 0, 1. And this point on the x-axis is 1, 0. So this line has an equation of y equals 1 minus x, just based on point-slope form. I hope that makes sense to you. Okay, then it says express the area of the rectangle in terms of x. Okay, well again, area of a triangle is 1/2 base times height. The height is 1. Oh, the rectangle, express the area of the rectangle, sorry. Okay. This is the part that's confusing in optimization problems. When you have something inscribed in something else, you have to recognize that the height of this is whatever the y value is at that given x value. So this rectangle could look like this, or it could look like this. You don't know what the x value is to get the y value. So, but you do know that the equation of this line is 1 minus x. And you also know that the base of the triangle is 2x. Remember, if we're just calling this x, then the whole base of the triangle is 2x. So it's 1/2 times 2x times 1 minus x. Hopefully that makes sense. So now if we want to maximize the area of the rectangle. So area of a rectangle equals length times width, or in this case, 2x, because remember, we only talk about x being from here to here. So area is 2x times y. But we know that y equals 1 minus x. So let's distribute that. Take the derivative and set that equal to 0. So x equals 1/2 and y equals, if x is a half, y is a half. If you plug back into here. All right, so that was all the parts of that question. I know I didn't explain it very well, but I'll be able to explain it better in class if you didn't follow that. Okay, let's try another one. The largest rectangle. Number 6. A rectangle has its base on the x-axis and its upper two vertices are on the parabola y equals 12 minus x squared. So here's what it looks like. Here's 12 minus x squared. Here's the x-axis. These points are 0 and 12 because we know 12 minus x squared. That doesn't make sense. No. The y-intercept is 12. It's based on the x-axis and its upper two. This is 12 minus x squared. Okay. So we need x by y. We want to maximize the area. Area equals xy. But again, y is 12 minus x squared. And is x 2x? Let's think about that. If we're talking about this point as being where x is, then the base has to be double that. Yes. Right? Because if x is 1, y is 11, 12 minus 1. But the area of the rectangle is 11 times 2, because you have to double the x because it goes the other way as well. So let's distribute this and take the derivative. Set it equal to 0. Subtract 24 from both sides. Divide by -6. X equals 2. And y equals 8. Wait, where did I get 2? What did I do wrong? 24x minus 2x cubed. Oh shoot, maybe it was just x. 12x minus x cubed, 12 minus 3x squared. X squared equals 4. I still get x equals 2. Oh, right, silly. X is 2, so the base of the rectangle is 4. And the height is still 8. You just have to remember that when you're talking about a curve, the x value is only from here to here. So the base of this rectangle is really 2x. So once I solve for x, that's only half of the base of my rectangle. Okay, one more problem. Number 10. A 216 square meter rectangular pea patch is to be enclosed by a fence and divided into equal parts by another fence parallel to one of the sides. So we have this big guy, and there's going to be another fence here. Now, what do we know so far? We know so far that LW equals 216. The area is 216. And divided into two equal parts. Oh, I lied. These two parts are equal. By another fence parallel, what are the dimensions of the outer rectangle that will require the smallest total length of fence. What are the dimensions of this that will minimize the perimeter, the amount of fence? So let's label what we know. We know this is W. We know this is L. We also know that we want to know how much fence we need. So normally it would just be 2L plus 2W. But here we have another length of fence right here. So the L is really 3L plus 2W. And we want to minimize this. Okay? But I have two variables. So I need to solve this equation for either L or W. Doesn't matter. Let's solve for L. L equals 216 over W. So now my equation is 3 times 216 over W plus 2W equals P. Now if I take the derivative, P prime, I have to do 3 times 216, 648 over W. So let's think about that as saying 648W to the negative 1. I hope that makes sense to you. So the derivative of that is negative 648W to the negative 2 plus 2. Derivative of 2W is 2. And we want that to equal 0. So I want negative 648 over W squared plus 2 to equal 0. Negative 648 over W squared equals negative 2. Multiply both sides by W squared. Divide by negative 2. $324. And W equals 18. Which makes L equal 12. And so the dimensions of your outer rectangle would be 18 by 12. And the total length required would be 12 plus 12 plus 12 plus 18 plus 18, which would be 72 meters of fence. So basically, you have to try to rewrite the equation in terms of one variable, take the derivative, set it equal to 0. The hardest part's getting the equations. This is kind of like related rates. I think it's a little bit easier, so we're going to spend at least another day on this, maybe 2, but hopefully at least got a good start, and I'm going to give you some problems to try at home.